Thank you. I am so happy to be back here at West Coast Number Theory. I am particularly happy to be talking on the in-person day. I have so much missed being able to talk to a live audience. It has been 3 years and 1 day since I last did so, so I will let you guess what conference that was at. Yes, so today I'm going to be talking to you about how to find a widely digitally delicate prime. First, a couple of definitions. Digitally delicate prime is a prime where if you change any one of its digits, you no longer get a prime. And so the smallest one is 294,001. So you can verify this by checking each of the digits and each of the 9 possibilities you could do. I am not checking all of them, but just to give you a flavor of it, here are changing the last digit to a 3 gives you something divisible by 3. Changing the penultimate digit to a 1 gives you something divisible by 41. And I think I did this so that they're all co-prime. So way of amusing myself while preparing the talk. So what's a widely digitally delicate prime? That is a digitally delicate prime where if you change any of the leading zeros, then the number is composite. So the example I gave before of the digitally delicate prime 294,001, if you change the 10 millions place to a 1, you get a prime. So that is a non-example of a widely digitally delicate prime. And if I gave you one right now, my talk would be pretty short. So let's keep going. There's a theorem due to Michael Felicetta, who is right over there, and Jeremiah Southwick, who is not. And it's sort of a, I don't know, I think it's one of these very surprising theorems when you first hear about it, that a positive proportion of the primes in base 10 are widely digitally delicate. And there's I think I have a little bit of time. The talk would be short otherwise. I want to say something about for those of you who don't know what a covering system is. It's, I think, one of my favorite number theoretic concepts. So one might imagine so a covering system is a set of congruences such that every integer is satisfies one of the congruences. And the way it gets used here is you might say, okay, if I add 10 to the 15th to any number, then then if that number is, say, 5 mod 7, then 10 to the 15th falls in this residue class, and so I've forced it to be divisible by 7. For a clearer explanation of that, you can look at the Felicetta-Southwick paper or many others in this series of research. And then you know, some of the magic I won't get into right now is the showing that a positive proportion of primes in this congruence class is digitally delicate. And in the paper, they said, we do not know of any examples of widely digitally delicate primes. And this paper got some press outside your usual mathematical venues. there's a YouTube video with a theme song on it. But I think one of the things that is so amazing is here are the, a positive proportion has this property, but it is very difficult to exhibit anything with that property. And they stated in the paper that you'd be testing integers of size over 20,000 digits for primality, and even just using the pseudo primality test on them to generate candidates for this would be much too time consuming. I think for integers of general form, the record size for primality testing is around 30,000 digits for primality proving, I should say. And so this did seem daunting, but that being said, they said that it's almost reasonable to construct a widely digitally delicate prime. And I read that and I said, okay, let's see what we can do. Because I like doing things that are almost, but not quite reasonable. So I turned to the power of internet nerdery for this. So the covering system uses factors of the nth cyclotomic polynomial evaluated at 10. These are also factors of rep units. So rep units are numbers consisting only of ones in base 10. And if you look at 10 to the n minus 1, that's a string of nines. You divide out the nines, that's a rep unit. And so cyclotomic polynomials are factors of this. And there's this weird thing that's been happening to me in recent years where I do research and I think it's not about rep units, but then all of a sudden they pop in there. A colleague of mine, Hester Graves, and I wrote a paper on rep units that are Sophie Germain primes. They've popped up in other places. And so imagine my delight when I was perusing the books in the back of the room, and I found this book of John Brillhart's rep units and repitends, which I haven't, the second one I haven't had a chance to read about, but there's even a nice little note to the author that he gave this to John. So those of you who are perusing the books, I think I've had a little bit of fun opening up the front covers and seeing, more than just the book as a math book, the book as a piece of number theory history. So continuing on, so rep units are very popular on the internet with nerds. Another thing that internet nerds love to do is they love to factor numbers. And so we put those together and harness the power. And someone named Makoto Kumada runs a website that collects many of these factors. And so since the covering system was using factors of these, I could take these factors from the website and plug them in to the covering system. And there, in the original paper, there are 23 different primes where, to prove the existence of this covering congruence, you know that if you have a composite, you know it has at least 2 prime factors. But even if you don't know what the factors are, you can write this down, and getting around that is what sort of ballooned the congruence to 20,000 or more digits. if you have these explicit values, you don't have to get around this. And it turns out that of these 23 primes, 19 of them had been found by various people and collected on Gamada's website. For the other 4 primes, I just note that well, just by example, the first unknown prime was a factor of the cyclotomic polynomial, the 12 cyclotomic polynomial where n equals 1210 evaluated at 10. This corresponds to a congruence in the covering system modulo 1210. Well, you can cover that just as well by replacing 1210 by 605. And so there's an additional factor of 605 there. For another one, modulo 1210, we replace it by a composite factor. There's nothing in this construction that requires things to be prime. Just as an aside, some of these things will make more sense if you read the Phillips-Southwick paper first, which I highly recommend. The paper, what I am talking about now, is available. What I wrote is available on the archive. So read their paper and then read my paper. And there are a couple other examples. And so the code for this is on GitHub. First, there's a massive use of the Chinese remainder theorem. That's just a quick Paris script. And then you're checking, now that you've got these explicit values, now you're only checking things for pseudo-primality, probable primality around 4,000 digits, which is much more doable. And so you find something that's a probable prime. And then if any of the, you check all of their changed digits, because it's in the congruence class, you know what the deal is with the leading digits. So you just have to check the non-leading digits. That took about 400 CPU hours. And then Paris has this built-in primality proving, and it took about 30 CPU hours to do that. And then how do we know I did not make a mistake? Oh, well, first of all, here's the prime in all its glory. What? It shouldn't be. So how do you verify it? Well, every modulus is a factor of this. I misspelled congruence. Blame Kylian Mbappe for not giving me time to double check my slides. And then I verified that if you add 10 to the j for any of these, there's a non-zero GCD with the congruence modulus, just showing that this is going to give you the widely digitally delicate things. And if you're paying really close attention, or possibly if you were the referee for this paper, you'd say, wait a second, you need to check this for each of the 9 digits instead of just that. And so yeah, you need that D in there. And when I did that, there was a mistake. So the verification was not complete. So everybody, buy your anonymous referees a beer if you can. And this is the actual answer. So be sure to check out version 2 on the archive. And that is what I have to say today. Thank you. I remember how many digits are in the wrong one. The wrong one is 4030, and this is within 10 or 15 of that.
Do you have any questions for John?
So a great example of the importance of verification is how many hours for the verification. Is that it still seems like a pretty big verification, but shorter than 300 plus hours. Is that right?
Yeah, it ended up being. I think it ended up being maybe. Less than a day for each of the 9 digits. But I did not really optimize that other than when it was several days for each of the 9 digits, not doing something stupid that slowed it down.
So this would not be one of those classic examples where verification is fast and computation is slow. Verification is still pretty slow then. Is that fair?
Yeah, but I don't know how slow it would be if I really worried about that. Verification is definitely faster, because it was only 9 CPUs for I don't know, 10 hours or something each. So that's faster and could probably be smarter if, for example, these computations were done with the PRI library and the verification was done with the command line calculator. So that could have been sped up.
May I ask one more question? I'm curious which primality proving technique you used.
DPP.
Yeah, do we have any other questions?
This is going to be a non-traditional question because I'm going to ask it of a member of the audience. Michael, weren't you wearing a shirt with delicate primes on it yesterday or?
Yeah, that was, yeah, not the widely, but digitally done.
Okay, do you have any other shirts that apply to additional talks that might happen today?
So, related to Michael's clothing, when I found it, I thought, well, wouldn't it be funny to print it on a t-shirt and just mail it to Michael with no explanation? And I actually looked into it, but it got to be too complicated. And I'm really glad I didn't, because it would have had the wrong prime.
It would also probably need really long arms.
The font would have been fairly small.
Yeah, are there any other questions?
Yes.
So Carl asks,
So,
are there infinitely many primes that are not widely digitally delicate?
It's a, he says that question. It's very fascinating.
It's not known. Carl's asked that question. It's a very interesting question. It's an unknown question.
Gary, would you like to suggest that somebody raise that question at a problem session?
Sure, I mean, given your ask, is it possible that all sufficiently large columns are widely digitally developed?
That would be the same with us.
Well, okay, I must have misunderstood what Carl's question was. Okay. All right, yeah, okay, yeah, then it is the same thing as I was thinking.
I should note from the original paper, these techniques are specific to base 10 and also apply to other bases, but not all of them. There were formulas given in there for bases below 10 that were a very nice warm-up computation for me to make sure that my code was not crazy. The error was I was cutting and pasting factors between 2 different things, and I just pasted wrong. But the verification, if done correctly, catches it. So.
all right, let's thank our speaker again. Please.